Welcome to the Leica SP8 tutorial of the Cell Imaging Facility Core at the Cross Cancer Institute. This tutorial provides you with the instructions for basic use of the Leica SP8 for confocal microscopy. If you are the first person to use the Leica SP8 for the day, follow the provided startup instructions. Remove the cover from the microscope body and place it in the provided bin. Do not put it on the laser or any other equipment. The previous user should have left the 10x objective in the active position, but check this before every startup. If it is in the 25x or higher, you will have to change it to the 10x once all hardware started and before initializing the stage through the software, or the objective will crash into the stage. Start the software by double-clicking the LASX icon on the desktop. For basic confocal microscopy, select the second configuration. That one encodes the multiphoton laser to be off. Make sure resonant and stead are turned off and the CIF system settings are selected. Then you should see a warning about the microscope stand, asking if you want the stage of the DMI-8 to initialize. Before you click yes, make sure the 10x objective is in the active position or the stage will run into the objective lens. You only have 1 minute before it defaults to not initializing. Make sure you are at the setup until the software is loaded fully. This will take a couple of minutes. Sometimes a warning about the minimum distance of 8 nanometers will pop up. This is not always the case, but nothing to worry about, just click OK. Once the software loaded, you will find all essential settings for your acquisition on the left side. Going from top to bottom, there are several acquisition modes you can choose from. By default, the XYZ mode is loaded. This is the main mode for most experiments. In the XY sub-window you can first select the format of your image in pixels. 512 by 512 is a commonly used size, but 1024 by 1024 is typically required for publication. For demonstration purposes we will stick with 512 by 512. Next, you can select from a variety of options. The scanning speed will affect your pixel dwell time and you will likely jump between a faster and slower scanning speed when scanning live and adjusting your settings versus when you are acquiring your image. Then, the bidirectional scanning will make your scan faster when activated but at the expense of image quality if the phase X slider is moved. Since there is no way for you to calibrate this setting except visually inspect carefully the resulting images, either avoid using it or make sure the slider is in the right position, as previous users' adjustments to it will remain active. Another very important setting is the zoom factor, which will directly change your pixel size. Furthermore, you can use line averaging, which will increase smoothing, similarly to frame averaging, and line accumulation, which is usually used in very dim samples. All these will alter your image quality, but you will see for yourself in a second. Another important section is tucked away in a drop-down tab. The pinhole is conventionally set to 1 ARI unit, and you should make sure that this is the case, as right now for instance it was set to 3 AU, which would allow out-of-focus light to be collected. Click ARI 1 to set back to 1 ARI unit. The last of the left side options is the Z-stack, but we will talk about Z-stacks later. Finally, besides directly from the display of the DMI-8, you can also access the objective lenses through the software. However, please use this drop-down only as a reminder of the objectives and their immersion media, as those are not explicitly stated on the microscope display. After loading the software, you can load your sample. Since this is an inverted scope, your cover glass faces down. This stage gives very fast feedback and you need to be careful with it. Do not put any weight on it. One side of the sliders is secured while the other can be moved to slide your sample in and out. Move your sample to the outer edge of the holder and secure it with the movable slider. Move in X and Y with the controller such that the lens is facing your sample. Now, you can use the microscope display to start the fluorescence mode and focus on your sample using the oculus. To set up the light path, click on the icon with the little person next to the light spectrum. Here you click on the 3 dots and select one of the predefined dyes. We have a list of options, but if you can't find your dye, Select one that is closest in excitation and emission to the fluorophore you are using. Next, typically use a PMT for DARP or other short wavelength dyes, as those are often very bright and do not require the higher sensitivity of a HYD detector. For the other fluorophores, simply use the HYD detector. Then, select the scanning mode that will cause the least crosstalk between your channels. The line sequential has the benefit of allowing you to see all channels simultaneously during scanning. Loading these settings will add a sequential scan subtab on the left side. Start the live mode. Find your focal plane, and keep adjusting laser power and gain until you have a good image. Usually, we want the view on the right to be in over-under mode, so that we can spot over or under saturated pixels. The heat map is rather reversed in this system where blue indicates oversaturation. To manipulate laser power, you have to select the respective sequence in the bottom left sequential scan section. You can drag the laser power slider, double-click on the number and type a specific number in, or scroll with your mouse after clicking on the slider. Always keep in mind that you should only be changing the laser power of the laser in the respective sequence. By default, the other lasers will show 0 laser power. If you, for instance, select Sec1 but add laser power to the laser in Sec2 as well, you will be producing crosstalk between your channels. To change the gain, you need to click on the respective image and use the USB controller. Keep adjusting laser power and gain until you are happy with the image quality. You can find the overlay icon on the right next to the image view. Now, let's adjust the XY parameters. After selecting your channels, the system is now able to calculate the optimal pixel size for your conditions. Click the optimization icon and pay attention to the changes this will apply to your pixel size. Leica will also suggest a particular format, but you can still choose your own. After bringing back the format to your desired dimensions, only make sure to adjust the pixel size back to the number that you have gotten after pressing the optimization icon by adjusting the zoom factor. Now, let's explore how different adjustments will modify image quality. First, we scan at a high speed and apply no line averaging. Every time you want to take a 2D image, click Capture Image rather than Live. This will add that image to your current project, which you can find under Open Projects. Next, we lower the scanning speed, thus increase pixel dwell time from 0.8 to 1.58 microseconds. You can already appreciate the improvement in image quality. Now, let's add line averaging and start with 4 lines. Averaging removes random noise and smooths your image but also slows down acquisition, as now every row of pixels is scanned 4 times. If we push averaging now to 8 lines, the improvements are marginal but cost us a lot of time. Let's zoom into the acquired images and compare the conditions. When starting off with a new experimental condition and setting up your imaging requirements, we recommend to take images from different samples in various spots with varying acquisition variations before settling for specific settings. Make sure to disable smoothing in the image viewer to see your real raw image. One commonly used feature of a confocal microscope is the Z-stack. There are 2 ways to set up your Z-stack. For the first approach, you need to know how big your Z-stack will be in the end, which will be based on the sample depth. Pay attention to the Z position for that while finding the outer limits of your sample in Z direction. It looks like these cells are roughly 15 micrometers in diameter, thus you can define the whole stack to be somewhat bigger than that, let's say 20 micrometers, and click recenter when you're back in the focal plane. This will ensure that your focal plane will be imaged as well as 10 micrometers above and below the focal plane. Expanding the Z-stack with the magnifying glass gives you a visual representation of where your focal plane currently is and how large your Z-stack is. The step size can either be automatically calculated or determined by you as either step size in micrometers or in number of steps. The latter will determine how much time you will spend acquiring the Z-stack but is otherwise fairly irrelevant for resolution. The actual step size, though, will make or break your resolution in Z direction, which is already not that great when compared with XY resolution. We can take advantage of the system-optimized suggestion when setting up our conditions, but for comparable results across samples the step size needs to be identical in your final setup. In order to start the ZStack acquisition, we need to click on Start. After a few seconds, the system will have calculated how long it will take to acquire your ZStack and display the time at the bottom of the window. The second way of acquiring a ZStack requires you to define the upper and lower boundaries yourself. Simply move out of focus in one direction, click Begin, then move through the cell out of focus in the other direction and click End. Both methods have their use cases, but you will likely benefit from the first one as that one allows you to make sure you are capturing the in-focus plane that you center your stack around. Finally, the little garbage bin icon will delete your ZStack coordinates. One very useful tool is the navigator, especially when you work with tissue and are looking for a specific structure or when your marker of interest is spread out and/or rather sparse. Open the navigator by clicking the grid type icon in the top left of the acquisition mode settings. In navigator mode you have access to all previous settings including the beam path, which at this point you shouldn't be needing to modify anymore. The scan mode and ZStack settings, however, you might want to change while in navigator mode. The navigator will by default scan at a 600 Hz speed, but you can further increase that for the sake of time. Use the spiral button to perform a large, fast overview scan. To add more fields of view in a more targeted fashion, go to the area you're interested in and double-click there. This will acquire a live scan in that area that is part of the overview. Scroll with the mouse to zoom in or out and drag the image around to see areas of interest better. If you want to keep the overview, click on Save Overview and rename your overview image. From the navigator you can find this overview under Mosaic Merge. Since this is a fairly crude image, you can improve the quality by clicking Merge in order to stitch the panels together properly. This will also expand the image borders and fill empty space with a black background. As mentioned earlier, the navigator will make your life easier when your regions of interest are spread out. Select the plus icon and click on the areas that you want to image. The task list on the right-hand side will populate the areas of interest you selected. Once the task list is populated, you can review your selections by going through the list. If you made a mistake with a selection, simply click on the X in the task list to remove that selection. Directly from the navigator you are able to start your image acquisition in 2D image or 3D. If you increased your scanning speed, make sure you go back to the desired settings. We will acquire ZStacks in those two areas but reduce the ZStack volume to speed things up as this is only a demonstration. In the top bar, you can toggle the available channels on or off. If you are staying in the navigator and want to look through your acquired images, you can do that under Mosaic Merge and the Open Projects list again. Before moving to the next area, we recommend deleting those areas of interest from your task list, as the navigator will image all areas that are in the task list when you start your experiment. When closing the navigator, you will not lose the memory of the previous overview, nor will the overview itself disappear until you actively delete it from the images list. For now, we keep this overview image and use it to find our area of interest again after switching to an immersion objective. Switch the objectives through the microscope display only. When switching between objectives with differing immersion media, the display will blink and wants you to confirm the switch as you might have forgotten to remove oil or water before switching objectives. Remove the sample and apply 2 drops of water to the objective without touching the lens. Place the sample back in the holder. Since you will have to move your sample to apply the immersion medium, you will lose your exact spot. To find that spot again, go back to Navigator after switching your objective. As you can see, we manually moved back very close to the area we've been working in previously. When we acquire a fast snapshot, we can see that we are off by only a little with the 25x compared to the 10x. As you've learned in your theoretical modules, different objective lenses will be able to collect different amounts of light. This means we need to adjust our imaging parameters again. For this, let's go back to an area that contains cells and close the Navigator mode. For now, we discard the Z-Stack settings and collapse that tab. Starting with Sec 1, let's adjust the first channel. Although the DARP channel does not seem saturated, we also don't appear to be in the right focal plane to judge this. While channel 2 is clearly saturated, remember blue means saturated in this heat map, channel 3 looks okay, but again, we have to find the right focal plane first. Since we are adjusting the spectral settings, we change the scanning speed back to 700 for a faster live view. Quickly, we see that we were in the wrong focal plane. Now let's adjust the laser power and gain to avoid oversaturation and find the best signal to noise ratio we can get. Since we explored the sample with the 10x already, this should be a rather quick process. Technically, you could start with your desired objective lens right away, but especially in the beginning using a lower magnification can help getting a solid overview. When we compare the same settings we explored in the 10x, now with the 25x, the bump in NA going from 10x to 25x visibly improved the resolution. Now, let us find a fresh area and the right focal plane to acquire another Z-Stack. The system-optimized setting would be 600 nanometers thick slices, but we change this to 400 nanometers. Although, the system knows its own optics best and can calculate Nyquist for you, Leica only gives you the best option for one channel effectively. With 400 nanometer sections, we sample at a higher rate than the system-optimized setting, as slightly oversampling will help us if we wanted to deconvolve those images later while avoiding potential undersampling in our channel of interest. Although we increased the sampling rate by reducing the step size, the time we spend scanning was not overly inflated and well worth the gain. Click on the 3D icon to see the 3D reconstruction of your Z-Stack that opens on the second screen. As with the 2D view, you can split the channels, show an overlay, zoom, and rotate your stack. Finally, we want you to be aware of Leica's automatic deconvolution tool, they call lightning. Most settings are identical to the confocal settings under TCS SP8, but you also get the lightning slider and the lightning settings. When the slider is activated, you will notice that some of your XY settings become unmodifiable. And when dragging the slider either towards speed or resolution, these XY settings will change. Since you want to be in control of your experiment, you don't use this automatic tool but rather adjust your settings as needed for XY. Also, make sure to add your mounting medium under the lightning settings section, as this will apply the refractive index of it to the deconvolution calculations. If you cannot find your particular mounting medium, look up the refractive index of it and add the value yourself. Trying to reapply our previous image acquisition settings will not work in lightning mode. So we switch back to TCS SP8, or confocal mode, and reapply the settings. After switching back to lightning, we adjust XY to our desired format, since this is a setting that won't be adjusted when using apply image settings. We find our focal plane again and recenter our Z-Stack. Now, we can start the experiment and acquire our confocal as well as lightning stacks at the same time. In some instances, using lightning might even speed up your Z-Stack acquisition. In your project, the first file under the Lightning dropdown is your regular confocal stack, and the file with an _LNG suffix is your 16-bit Lightning stack. Comparing these two in the 3D viewer shows the further improvement in image quality after Lightning. If you need to resolve small details in your sample, Lightning might be the right choice. We just want to emphasize, however, that you need to keep an eye on any artifacts this post-processing can introduce, which should not be an issue if you don't violate Nyquist conditions. Once you are done with your session, double-check that you are not the last user for the day in PPMS. If someone booked after you or it is early in the day, we just ask you to keep the system running. Save your project on the E drive and in the stead_userdata folder. Find or make a folder for your lab and a subfolder for yourself, and save the project file in your folder. This file contains all information including images and metadata and can be downloaded from one of the workstations. There are no USB ports on this imaging computer. After saving, close your project and leave the LASX software running and log out of PPMS. However, if you are the last user for the day, simply follow the provided shutdown procedure. Finally, remove your sample and clean the objective with lens paper if it is an immersion lens. Never use any other tissue paper on the lenses. Remove a sheet of lens paper without touching it in the middle. Fold it twice and remove the water from the lens. Never press on the lens itself. Turn the turret back to 10x for the next user. If you choose to use the oil immersion lens, apply the oil to the cover slip instead of to the lens. Do this next to and not above the microscope. The 100x has a much smaller working distance, so be careful when loading and removing the sample. The oil cleanup is similar to the water immersion lens except that this is somewhat messier. After tapping off the oil from the lens without pressing on it, use the same lens paper to carefully remove excess oil from around the lens. Use as much lens paper as needed. As always, bring the 10x back for the next user.